So if we want to find an exponential model when we're given two data points, we use the following formula. A naught is the initial value. Then we look at the ratio of the amount at the second data point over the amount at the initial data point, and then we raise it to t over n. So if you look at the 2 points, 0 is at time 0 in the initial amount in the account. N is some unknown number of years later, or in this case it would be known number of years later, and then the amount in the account at that time. So let's see how we would actually work with this. So it says a certain type of bacteria was measured to have a population of 23,000. 4 hours later, it was measured to have 111,000. Answer the following. Write an equation that models the size of the population t hours after the initial measurement. So the first point says, well, at time 0, we had 23,000. And then 4 hours later, we had 111,000 bacteria. So this is our point 0 A naught, and this is our point 4 111. So using this model, P of t should be the initial amount of 23 over the new amount of 111 divided by the initial, and it's t over 4. B says we'll find the hourly percentage increase. So what I want to do is I want to find the rate. So this is b raised to the t over 4. So I'm only going to isolate this part of the equation. And then what I'm going to do, I'm going to leave t out of it. And I'm going to say, well, I really want to know what this number works out to be, because this raised to the t gives me this. And so whatever this value is here, that's actually b, my growth factor. So if I get my calculator back out, I can say, well, 111 divided by 23, close the parentheses. Now this is important. This is a fractional exponent. I can't just say 1 divided by 4, or else it will raise this to the 1 and then divide the result by 4. So I actually have to open parentheses for my exponent. And when I raise this all to the 1/4, I get 1.48217. So I'm going to take this out about 4 decimal places. And when I round to the 4th decimal place, I get 1.4822. So that's B. That's the growth factor. But it actually asked me to find the hourly percentage. So I need to write this as 1 plus my rate. So if you remember in the previous problems, we were given the rate in percentage, converted it to decimal, and plugged it in. Now we're just going to reverse the process. So I'm going to take this percentage in decimal form and now write it as a percentage. So the rate is actually 48.22%. What is the size of the population after 10 hours? So that's just saying plug 10 hours into our model. So P of 10 is going to be 23 times 111 over 23 raised to the 10 over 4. So there's actually 2 ways we can do this. We can type this into the calculator directly, or if I peek ahead, I see that it's going to ask me to figure out the doubling time. So I'm going to need to put the model in the calculator anyway. So let's look at kind of a way to use our calculator to do this. So if I go to y equals, clear everything out, I'm actually going to put my model in the calculator. And once again, when I raise this to an exponent, that's a fraction, I have to put that in parentheses. So it's x divided by 4, close parentheses. So when I go to graph this, right, everything's over here on the left side. So I'm going to, I want to check this after 10 hours. So I'm going to go back to my window, and I'm going to set this up to go from 0 to 15. And then I'm going to go to zoom fit, so I can get a little bit better view of the y values. Oops. And so you can see it starts going really quickly after this point. So in the calculator, since all I wanted to do was plug 10 into the function, I can go to second, calculate value, and it will let me type any value I want, and it will give me the corresponding y. So we can see it's 1,176.835, right? So remember, this is in thousands. And so I can say that this is 1176.835 thousand bacteria. If I typed this into the calculator directly, I should get the same answer. So if we do 23, 111 divided by 23 raised to the 10 divided by 4, I get the exact same number. So if you've got to use the model in your calculator, second value is really useful. So D says, well, what is the doubling time of the population? So we want to know, well, when does our model equal 46? Because the initial amount was 23. So I'm going to set 46 equal to this. And look what's going to happen. Exactly what I said in the previous problem. If I actually use these numbers, well, I can divide both sides by 23. So 23, and when I divide over here, you just end up getting 2. So all you have to do is set 2 equal to the factor rate part of the problem, and the initial amount should cancel out. So I've already put my model into my calculator from the previous part. So now let's set this equal to 2. And I'm going to go to zoom fit. So there's the model, there's 2, and so now if I go to second, calc, intersect, there's my first curve, there's my second curve, and when I guess, it's taking a second. So we're getting an error, so we must not be quite on the screen. So let's go back to our window. We've got this set at 0. I'm going to take this down to 5, and I'm going to adjust my Y scale from 0 to, let's say, 5, because we're only looking at it from 2. So let's graph it again. Oh, I think I know the problem. I didn't remove the 23 from the model, right? Because we said the 23 is gone. So I'm just going to delete the 23, and now let's try it again. There we go. So there's the model. And there's 2. So we're going to go down to intersect. First curve, second curve. And we get about 1.76 hours. So make sure you're paying close attention to your units when we're doing these problems, because you want to make sure that the units are matching appropriately in the problem. Also, it'll help you make sure you're solving for the correct variable.